In this video, we're going to continue talking about polynomials. First thing I want to do is focus on solving polynomial inequalities. So let's say for this example, we're interested in solving this polynomial and wanting to know where it is greater than 0. So the way I like to do this is I basically am going to find the zeros for this polynomial, find the horizontal intercepts. That's what we've been looking at before. And I'm going to graph those on a number line. So the first 0, which we've been horizontal intercepts up to this point, is x equals -3. That's from the first factor, right? X plus 3, setting it equal to 0 is going to be x equals -3. The second factor would be x equals -1. And the third one is x equals 4. Now, technically, x equals -1 has a multiplicity of 2. But for finding a 0, it's just listing it twice, and there's no reason for me to do that. So what I want to do now is I want to graph these on a number line. All right, so here's 0. 1, 2, 3, 4, 5, 1, 2, 3, 4. Okay, that's fine. All right. So let's see. -3 would be right here. -1 is right here. And 4 is right here. And here's what I'm going to do. I'm going to divide each of these portions of the number line up into regions. And what these regions represent are possible answers to this inequality. So the first region is going to occur for all the numbers that are -3 and below. So all these numbers here, -3 off to infinity. Region 2 is all the numbers between -3 and -1. Region 3 are all the numbers between -1 and 4. And region 4 are all the numbers bigger than 4. So going off to positive infinity. And what I'm going to do is the process I'm going to use is I'm going to test the numbers from each region. And what I'm going to test them in is this original inequality. I'm going to plug those number values for x into there. And I'm going to see, does it come out to be bigger than 0? If it comes out to be bigger than 0, that means I'm going to get a positive number, and that is part of the solution. If it comes out to be less than 0, I'll get a negative number, and that would not be part of the solution. So let's go ahead and try this. It helps to see what I'm talking about. So from region 1, I want to pick a number on this number line that's less than -3. So you can pick anything you want, -10, -20. You could pick right next to it. Let's pick -4. I see that -4 is in that region. So I'll pick -4. So what I'm going to do is I'm going to plug -4 into the highlighted thing. So that's going to give me -4 plus 3, -4 plus 1 squared, and then -4 minus 4. Okay, so -4 plus -3. I'm sorry, -4 plus 3 is -1. -4 plus 1 is -3 squared. And -4 minus 4 is -8. All right, and if I plug that into the calculator, let's see, that's going to be 9 times 8, which is 72, and it's going to be positive because the -3 squared, it's going to become positive 9. And then the -1 and the -8 are going to become positive 2 number, which means that this region, the region that 1 represents, this region here on the number line from here to here, is part of my solution. All right, let's check region 2. So let's pick a number in region 2. So region 2 is between -1. So to me, the perfect number to pick would be -2, right? This number right here, right in between -3 and -1. Like, yeah, that works out really well. Okay, sorry, that's that because that was such a sad -2 right there. All right, so I'm plugging -2 into the highlighted thing. -2 plus 3. -2 plus 1 squared. -2 minus 4. Okay, so let's see. That's going to be 1, and that's going to be -3, and then that's going to be -5. Okay, so let's see. That's -1 squared is 1 times 1 is 1 times -5 is -5. Comes out to a negative. So it's not a positive. Therefore, this region is not part of the solution. So I just crossed it off. Okay, region 3. Let's pick a number in between -1 and 4. 0 is my favorite number. I always pick it whenever I can. It makes my life easy. So I'm going to pick 0 since it's in that region. And we have lots of options. You could have picked others, but 0 is the nicest. Okay, so let's see. We get 3, 1 squared, and then 0 minus 4 is -4. All right, so let's see. That's going to give me 3 times 1 is 3 times, okay, -12. So that's not part of the solution. It's not a positive, came out negative. So region 3 is not part of the solution. All right, try another one. Last one, region 4. Picking a number that's bigger than 4. Let's pick 5. 5 plus 3, 5 plus 1 squared, 5 minus 4. So I can already tell all of these are coming out positive. In fact, it's okay if you like stopped and you're like, cool, I'm getting a positive number. That's part of the region. Like there's nothing wrong with that. Okay, so let's see. 6 squared, 36. 36 times 8 actually comes out to 288. And it's a positive. So this is part of my solution. Region 4 does work. So all of these numbers over here are part of the solution. So if I want to write my answer in interval notation, here's how it's going to look. -infinity up to -3, parenthesis, because we're not interested in it equaling these values, right? The inequality here does not have an equal to sign. So I'm going to use a parenthesis. So even though I drew closed circles, really open circles, okay? Really, they're open circles. So -3, and then the other one would be from 4 to infinity. Cool. Okay, so that's kind of the old school way of doing this. I like it. It's pretty straightforward, very visual. That's how you could double check. The other way is to actually sketch the function on the calculator. And what you'd be looking for is when the function actually has positive y values, okay? So let's use this example to try to show that. We will find the domain of this. Now for a function that has a square root, I use under the square root. So really what I'm wanting is I'm wanting this thing under the square root to be bigger than or equal to 0. That's in essence what I'm trying to solve. Bigger than or equal to 0. Okay, so if I look at the graph, there's a couple ways to do this. This is actually a quadratic function because it's got the squared. So I could go ahead and factor this thing. Let's do that. So let's see. I'm gonna reorder it first. -t squared minus 5t plus 6. And then I'm going to factor out a -1. Okay. So that's going to be t squared. Wow, that's the saddest parentheses. T squared plus 5t minus 6. And then factoring that would be t plus 6, t minus 1. Two numbers that multiply to be -6, but add to be 5. It would be -6. I'm sorry, +6 and -1. All right, so there we go. So that's where the intercepts are going to be. So the intercepts, I'm going back now to the concept of horizontal intercepts, would occur at -6 and 1. So if I'm graphing this, then 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. That's fine. So here's what we got. It's going through -6 and 1. Those are the intercepts. And it's an upside down parabola because the leading coefficient is negative. So I'm not going to get too particular with the vertex right now. I'm just going to do a rough sketch. So very rough. That's what it's going to look like. And the reason I'm doing this is I just want to understand that visually, the positive part of this quadratic, what makes this thing positive, when we're saying that we want this thing to be bigger than or equal to 0, when we make this statement right here, these over here, what we're referring to are the y values. We want f of t to be bigger than or equal to 0. And f of t represents the y values. So the y values are going to be bigger than or equal to 0 whenever they're above the x-axis. So on the graph, that's all of these values, oops, right here. All of those values are representing positive y values. So basically, all the values of y that occur between the two intercepts. So the way I would write that then is all the values between -6 and 1, oops, wow, that was weird. -6 and 1 are going to work to make this thing positive. But I'm actually going to, in interval notation, use brackets because this has the equal to bar. So it's including those 2 points. And you're noticing that I'm listing the x values that make this thing positive. Just like in the last problem, I was listing the x values that worked. But visually, I'm looking at the y values to determine which x values work. So all of the y values paired up with the x values between -6 and 1 make this thing positive. You could have factored it, taken these test points and did what we just did in the last problem, where you find the number line and do the regions and test. Would have worked exactly the same way. All right. And there would have been only one region that worked, and that would have been between -6 and 1. Just so you know, both methods work, but there's the 2 methods you can use to solve inequalities. Okay, now I do want to also do one more thing, because we just kind of built on this idea this last example. And that is the idea that we can write our equations based on the intercepts. And we can graph the equations based on those intercepts, get a loose graph. So the factored form of polynomials can allow us to write an equation of a polynomial based on the horizontal intercepts. So how it's going to look, and we've seen this many times, is our polynomial f of x is going to be a, the leading coefficient, times these intercepts, x minus 1 squared, x minus 2 squared, and then we keep going this pattern until you list out all of the intercepts. Now they could have multiplicities, like of 1, 2, 3, 4, they could have multiplicities. So technically we have powers for each of these. So p sub 1, p sub 2, and p sub n. So they all could have individual powers. The powers might be a 1, they might be a 2, right? It just kind of depends on the multiplicity of the factors of intercepts. I mean, trying to erase that so I can make that a more distinct p. There we go. P sub 1. Okay, where the powers p sub I depend on the factor that can be determined at the intercept. That's such a weird way of saying it's the multiplicity. And you just write in that word. We've been using the word multiplicity. Okay, so here, let's show how we can actually look at a graph and come up with an equation just looking at the horizontal intercepts. So here we go. We got a graph. Let's look at the intercepts. So we have an intercept here at x equals -3. So here, I'm going to list out the intercepts. So x equals -3. We have another one at 2, and that one has a multiplicity of 2 because it's bouncing off like the parabola. So it has a multiplicity of 2. And then another one at 5. All right. So if I'm going to write this in factored form, I'm going to basically work backwards. So as a factor, this would be x plus 3. This would be x minus 2. And this would be x minus 5. And technically, x minus 2 is squared because it has a multiplicity. And this would be a potential equation for our polynomial. The only thing I don't know is a, what a would be possibly in here. So all of those intercepts are coming from the horizontal, all of those factors are coming from the horizontal intercepts. And then I'm putting the square just based on the fact that I understand the multiplicity of 2 kind of does that. It touches the point and then bounces off of it. Okay, so to find a, I basically pick another point in this graph that's easy to see and identify. And I like to use the y-intercept. So I'm going to pick the point 0, -2. So I'm going to plug 0, -2 into here for x and f of x. So f of x is going to be -2. That's the y value. And then x is going to be 0. A is what I'm trying to find. So I'm leaving it alone. and I'm going to solve for A. Okay, so let's see. That's going to be 3, negative 2 squared is 4, and negative 5. So that's 60. Negative 60, which I'm kind of running out of space, but that's fine. It's negative 60A. So if I divide both sides by negative 60, that's going to be 1/30. So that's A. So here, I'll write underneath the final answer over here. So f of x equals 1/30 times x plus 3, x minus 2 squared, and x minus 5. So that is the equation for this graph. So let's try that again. Let's look at all the intercepts here. So first intercept. Wow, sorry. First intercept. Such a sad I, whatever. X equals -1. And that has a multiplicity. So I'm going to list all my multiplicities too as I go. So this one has a multiplicity of 2 since it's bouncing. 2, x equals 2 is another one. And that has a multiplicity of 3 since it's curving through, kind of like the x cubed. Oops. The x cubed equation. And then the last one is at 4, x equals 4. Quick comment, I wanted to say this. So what I'm noticing, by the way, up for this is that the x's, I have 4 x's total. So there's 1 x, this is technically 2 x's, and then 4 x's. So 4 x's total, which means I have an x to the 4. Makes sense since my graph, right, the two ends are going upwards. So it makes sense that it's an even powered polynomial. And it makes sense that it has a degree 4 because it has 3 horizontal intercepts. So minimally it should be higher than degree 3 or degree 3 or higher based on the fact that there's 3 horizontal intercepts. So just to comment on that it kind of is consistent with some of the topics we've talked about before. Okay, sorry, here we go. And then x equals 4 is normal. Okay, so then in factored form, let me try to give myself a little more space here. Wow, I'm doing a terrible job writing because it's at the top of my screen. So my writing looks very, very sloppy. I apologize. I don't know the leading coefficient, but the first factor would be x plus 1 squared. It's based on the x minus 1. The next factor would be x minus 2 cubed. And then the last factor would be x minus 4. Okay, so let's talk about the degree of this polynomial. So since it's a multiplicity of 2 for that first x, that would be x, 2 x's, right? X squared. And then this would be x cubed. So there's 5 x's total now. And then 6 with the last one. Makes sense since this thing is going the same direction. It's going negative. So I already know that A is probably going to be negative, right? I know that information. It looks like it's at least degree 6. So let's go ahead and find A. I'm going to use the horizontal intercept at 0, -4 to plug in for my f of x and x. So f of x is -4. A is what I'm trying to find. And then 0 everywhere I see x. Okay, so let's see. That's 1 squared is just 1. -2 cubed is -8. And then -4 is the last one. So that's going to end up being positive 32 equals -4. Dividing by 32 is going to be, oops, not a negative. Sorry. Dividing by 32 is going to reduce to -1/8. So that's A. Makes sense that it's negative. So my final answer then is f of x equals -1/8 times x plus 1 squared, x minus 2 cubed times x minus 4. And there's an equation. Wow, that's a terrible box. There's the equation for this function or polynomial. So the last thing I'm going to talk about for polynomials here is estimating what we're going to call extrema. So extrema is the mathematical term for like highs and lows or extremes. But really what it is we're thinking of that as like maximum points and minimum points. And we've seen this when we talked about parabolas and we looked at maximum value of parabolas or minimum values of parabolas. That can work as well. So we've been calling extrema turning points. There are points on the graph that occur when you are turning direction from increasing to decreasing or decreasing to increasing. So that's what we've also called turning points. So let's look at an example of how we might deal with extrema, and we'll use technology on this one. So they created a problem here where we're going to construct a box from a rectangle that is 14 centimeters by 20 centimeters, and it's going to have an open top, so it won't actually have a bottom. And they labeled the rectangle for us, and the little cutouts, we're going to cut out these consistent little squares from each corner, and the idea is we'll bend up these little sides here, we'll bend them up, and those bent up sides will kind of form like a little open box. I'm going to do like a 3D version of what that would kind of look like. So that would be the little open box when they're all folded up nicely. Okay. Okay. So that's what we're going to be doing. So what they want to do is they want to find what size squares would maximize the volume for this box. So to find volume, let's talk about that, of a rectangle, a rectangular solid, is to do length times width times height. Length times width times height. That's an L. It's kind of a sad looking L. L, there we go. Length times width times height. So, or LWH. I don't really need to put the multiplications in there. There we go. So what we want to do is we want to figure out what the length, width, and height is for this box if we know that each of these cutouts that we're calling W. So based on that, then W down here would be the height of the little box, right? It would actually be the height of the box. This, we know, they told us that this length is 20 centimeters. And that this length here, they gave us that that's 14 centimeters. But we're removing W from both of those on either side. So what we're left with from here to here is 20 minus W twice. 20 minus 2W. That's the length of that. And then over here on this side, it would be 14 minus W twice, or 14 minus 2W. So there's my length, my width, and my height based all on W. So my volume then, based on W, is, I'll just write them out, W times 20 minus 2W times 14 minus 2W. All right. Let's multiply this thing out. Let's go ahead and come up with an equation because I'm going to use Desmos to finish this problem off. So I'm going to start by foiling, multiply those first, and I'll just deal with the W after. Oops. W sits out here. Okay, so let's see. 20 times 14, I got my calculator working, so that's 280. 40W minus 28W plus 4W squared, which when simplified is 68W plus 4W squared. And then I'll distribute the W in that's outside here, boop, into all three. So 280W minus 68W squared plus 4W cubed. There's my volume written out nicely. Okay, so what I'm going to do is I want to find a potential maximum point. I'm trying to maximize this equation. So I'm going to go to Desmos now, and I'm going to graph that equation. So let's do that. Let me go ahead and attach my keyboard. My life a little bit easier. I have the equation I graphed way earlier. Okay, so in another video, V of W equals, okay, so 280W minus 68W squared plus 4W cubed. All right. Wow. Okay. So it's so big, I can't even see the graph. That's all right. I can zoom out. Wow. All right. So as you can see, like it's zooming out, but the values are getting so big that the graph is looking very skinny. So I'm going to adjust this graph. And the way I do that is this little tool here, graph settings. I'm going to keep the Y's pretty big, but I'm going to change the W's values. Those are small. In fact, here, let me just look at the graph, right? Like they're like really close together. So if this is 50, right? That's 40, 30, 20. Like, okay, so how about I only go out to like maybe 15 on the x-axis, and I'm not even going to the negatives. I don't really care about negative values. So 0 to 15. I think that's more reasonable. I still don't see the top of the y values. How about I change that? Let's go up to, let's start with 250. Oops, still not big enough. Okay, let's go to 400. Actually, here, let me see if I need to apply it. Boop. Oh, okay. Here, sorry. Let me fix that. I apologize. So it didn't do 400. The y values, I'm doing the lower half right now. That's my problem. So let's go from negative 100. There we go. I was doing the wrong one, to 400. Gotta do the positives. There it is. Yay. Okay. I see the top now and the bottom. Okay. See a much better picture. There we go. So I had to adjust them. I kind of just based it off of trying, guessing. So the high point is what I'm after. I'm after this point right here. And Desmos is so nice that if you kind of click, it'll find it for you. 2.704 is the W that's going to work. 2.704 according to this. And then it'll give me a maximum volume of 339. So I'll just round that to 2.7. And then my volume, if they asked for it, is 339. So here, let me go ahead and switch back then to my notes to write that down. Take off my keyboard here. All right. So from the graph, or using Desmos, I'll put Desmos. I'm getting that W is 2.7 centimeters. That would be the best W to give me the maximum volume. Find the size of the squares that should be cut. Okay, so 2.7 by 2.7. That would be the answer. I just realized that that's how they asked the question. Find the size of the squares that should maximize the volume. So 2.7 by 2.7 centimeters would be the answer to the question based on the way they worded it. And I happen to see that the actual maximum volume is 339 centimeters from the graph.